I thought we were starting at 4:15. Everything's okay? Audrina, everything okay? Audrina? Okay. All right, folks, it's 4:16. I see we have 28 people. So I'm gonna give it another 2 or 3 minutes and then I'm gonna start. All right, I think we've waited long enough. So I'm going to begin now. Let's see if we can do 30 slides today. All right, you should be seeing my screen. Now, just to do a quick recap of something that we did on Tuesday. I spoke about the types of cells that you'd find in the alveolus of the lungs, right? I mentioned 3 types of cells. I mentioned a type 1 cell, which, as you know, is this one here. Your type 1 cell is your simple squamous epithelium. This is the one that makes up the bulk of the structure of your alveolus. This is the one that allows for gas exchange to occur because, of course, it is 1 cell layer thick, right? So that's the first one. So that is your type 1 cell. The next type of cell I mentioned was your type 2 cell. And these are cuboidal cells. We also call them surfactant secreting cells. And remember what a surfactant is. A surfactant is essentially a lubricant that allows the alveoli of the lungs to collapse and reinflate without sticking. Because remember, no, the alveoli are basically arranged like little balloons. And the idea here, of course, is that when you inflate the alveoli, because they're so clustered together, they press. Yes, go ahead.
So you said after the alveoli of the lungs collapse, what happens after before it sticks?
Yeah, that's what I'm talking about now. And by the way, when I say the alveoli collapse, I don't mean the lung is collapsing, you know. I mean collapse as in air leaves them. So they fall in on themselves like a balloon when you let air out of it. That's what I mean by collapse, right? Right? Now, when the alveoli expand, when they fill with air, they'll press onto one another, right? And without the surfactant, when they collapse, they stick to each other, which means that they're never able to fully properly collapse. It also means that when you try to reinflate them, they're stuck onto one another, so they don't fully reinflate either. Therefore, you cannot get enough air in or push enough air out to sustain the body properly. And that, of course, is why you need the type 2 cells. They make the surfactant, and the surfactant stops the alveoli from sticking to each other. Remember, simple cuboidal cells, type 2. The last one I mentioned was this here. I believe I also referred to the macrophage as a dust cell or a dust macrophage. And these guys roam around the inside of the lungs. They're kind of like a cleaning cloth, you know, when you washing a pot or something, and you have your little cloth and you're washing the inside, just roaming all around the inside of the pot, cleaning it. So the macrophages are roaming all around the inside of the alveolus, cleaning it. And of course, it's mainly getting rid of dust, hence why it's also called a dust cell. Okay? Now, that said, I want to talk about the blood-air barrier as well. Remember that when you breathe in, air at no point in time ever comes into direct contact with your blood. I mean, that would be crazy. First of all, your blood is under higher pressure than air pressure. So if there was an open pool of blood anywhere in your body, it would just squirt out. And also, of course, if you expose air to blood, bacteria, viruses, all sort of things will move straight into the blood, which is, of course, a bad thing. So you need to separate the air from your tissues, right? So you need to separate. So your internal space, which is in the lungs, needs to be a separate space from the space within your tissues, which would be in the blood, right? That is what the blood-air barrier is for. Now, what you're seeing here now is the major components of the blood-air barrier. So what do we have? We have the alveolus, right? We have the basement membrane. Then we have the cells of the capillaries. Then, of course, we have our blood cell membrane. So what we're going to do is we're going to count how many membranes that is. All right, I think I'm going to make this a little bigger. So it's easier for us to visualize and count. Because a question that can be asked is about the number of membranes that comprise the blood-air barrier, right? That's a question that we've asked in the past. And of course, past can come around anytime, right? Let me just take this out. All right, so let's see how many membranes a molecule of oxygen has to pass through in order to get inside your red blood cell, okay? Now, first of all, the oxygen molecule has to go into the simple squamous cell of the alveolus. So that is one membrane there, so. It also has to leave the simple squamous cell. So that's another membrane right there, so. It then has to pass through the basement membrane. And everybody knows that the basement membrane is from AMP1. So that's a third membrane right there, so. And that allows you to get down in the vicinity of the capillaries. And the capillaries are made of simple squamous tissue, just like the alveoli, which means you have two membranes here as well. One going into the simple squamous, one going out into the blood. So we're going 1, 2, 3, 4, 5 membranes so far. Then now the blood has to make its way into the red blood cell and across that membrane as well. Okay? So in total, we're looking at 1, 2, 3, 4, 5, 6 membranes. So oxygen has to pass through 6 membranes to get into your red blood cell. So blood-air barrier is a real deal, right? And of course, carbon dioxide now. Here's the thing. Sometimes carbon dioxide is carried by red blood cells, in which case it would have to pass through the full 6 membranes on its way out, but sometimes it's dissolved in the blood plasma itself, which means, of course, that it's only 5. You can imagine being asked a question about, carbon dioxide in the blood has to pass through how many membranes in order to make its way to the external opening or external spaces within the body, right? And of course, you have to say, boy, how many membranes this thing has to pass through. Remember, all right, so please keep that in mind. This is a very simple question, and people get it wrong all the time. For oxygen, it is going to be 6. For carbon dioxide is 5 or 6, depending. If it's the carbon dioxide is being carried by the red blood cell, that's 6. If it's dissolved in the plasma, that's 5, right? All right, hopefully that makes sense, right? And the last thing I'd mentioned to you on Tuesday was that the shape of the alveoli are not round, right? The shape of the alveoli increases the amount of space within them. So they're closer to being hexagonal than they are to being round. You can say that they have angles on them, right? And why do they have these angles? So that they can fit more efficiently without leaving spaces, right? Here's a nice hexagonal right here, so. Now, if we had said, okay, what if we made them round? You'd be like this. And all of a sudden, you have all of these spaces in between the alveoli, which would be of absolutely no use to the lungs. So it makes more sense to have the lung tissue have a more hexagonal shape to the alveoli than to be round, right? Round has the lowest surface area of pretty much any shape. So keep that in mind, right? So in the shape of the alveoli, not round, they're more hexagonal, right? Even here, you can sort of pick it up as well from this diagram here, that it is more hexagonal, right? All right. Now, let's talk about some stuff that you probably know already from CSEC. We're going to talk about how you actually breathe in and out. Now, oh wait, no, sorry, not yet. Let's describe the gross structure of your lungs, right? Now, I'm assuming everybody remembers what the term parietal and visceral mean, right? Parietal is lining a cavity. Visceral is lining an organ or gland. Basically, it's lining, right? So parietal lines a cavity. Visceral lines the organ or the gland. There are two types of membrane around the lungs. Lung membranes, as you know from AMP1, are called pleural membranes, right? And also from AMP1, you know that your lungs sit in a cavity in your chest called the pleural cavity, right? So far, this should all sound familiar, right? Now, the visceral membrane, of course, sits on the surface of the lung tissue. And the parietal membrane lines the pleural the pleural space, the pleural cavity here. Right? Well, I should say pleural space. Now, in between your visceral pleura and parietal pleura, both of those membranes are going to have a little space in between them, a tiny little space that is usually filled with lubricating fluid. So between the parietal pleura and the visceral pleura, you have a space. It's normally referred to as a potential space. Why is it potential? Because it's usually filled with a very, very thin layer of pleural fluid. And this layer holds the parietal pleura and the visceral pleura together. It's like, you know, when you put like a plastic bag down on a wet kitchen counter, or the plastic bag sticks to the counter because the water on the plastic bag helps to hold everything down. That is like what it is between the parietal pleura and the visceral pleura. They're sticking to each other because of the liquid, okay? But the liquid also acts as a lubricant. So when you're breathing in and out and the lungs are expanding and contracting, the membranes can slide over each other without getting damaged. So it is very important, right? So as it says here, the lungs can slide, but separation from the pleura is resisted like a film between two plates of glass. So you can slide around the two sheets of glass but it's hard to pull them apart, right? Now, I already mentioned this basic stuff about the lungs already, but let's run through. I think I said to you before that your lungs have lobes. And I even spoke to you about the importance of the lobes and the segments. But remember now, your right lung has 3 lobes. You have the right upper, right middle, and right lower lobe. The left lung only has 2. You have the left upper and left lower. So this is another case of asymmetry in the human body, where things are not perfectly bilaterally symmetrical. Now, there's also this right here, so it's not showing up very clearly, but if you notice here, there's this little curve here in your left upper lobe. This curve is called the cardiac notch because, of course, your heart sits right here. And because the heart takes up so much space, is one of the reasons why you only have 2 lobes on the other side, on the left side, and you have 3 on that side, right? Because the heart, you have to make space for the heart. Also, remember why the lobes are important. The lobes allow separation and isolation of sections of your lung tissue. So if one part of the lung gets infected with something, let's say, for example, develop an infection of the right upper lobe here, horizontal fissure between upper and lower. The infection can sit right here and completely mess up the right upper lobe without spreading to the other lobes, right? So you can pick up an infection in one lobe alone, or you can get emphysema, and emphysema is impacting one lobe significantly, and it's not really affecting the others that badly. So you can go in, for example, and have an operation and remove one entire lobe of your lungs. Let's say one of them becomes cancerous. You can just go in and have that lobe popped out, torn out, whatever, cut out. And the other 4 lobes will be perfectly fine without it, right? I mean, obviously, you won't be running marathons the way you used to, but hey, otherwise you're fine, right? So the compartmentalization of the lung and the division into sections allows for your isolation of pathogens if the lung does get infected. So normally when you get a lung infection, it's not the whole lung gonna be infected, right? There's also the reason why even things like COVID, for those who did suffer severely from COVID, it was the few bad-looking people who managed to get the virus in multiple lobes at the same time. And because of that, they got a bigger hit from the COVID. That's why we say that COVID is somewhat dose dependent for even those people. So even if you're 80 years old and you are of course in the prime target for COVID killing you, if you don't get a big enough dose of the virus, that the virus could have infected multiple lobes of your lung at the same time, chances are you will still survive. Which is why the death rate of COVID was pretty low, all things considered, right? Anyway, let's continue.
Sir, would that be
Yes.
the same thing for pneumonia?
Well, I mean, even pneumonia. Remember, listen, if you look at the actual corrected death rate for COVID, I think it was about double that of the flu, right? So it killed about twice as many people as the flu. It just killed them pretty much all at once. But guess what? What they haven't been telling you is that the death rate from the flu has been very low since last year to this year. You know why? Because the most susceptible people, COVID sought them out. So they didn't die of the flu, they died of COVID. So for the next year or so, or maybe a couple more years, flu death rate will be lower because of it. All COVID really did was pick the fruit young, right? These people were going to die eventually anyway. Right? That sounds really harsh to say, right? But when you're a 90
Very,
year old
sir.
who's been
Very
smoking for
harsh.
most of their life, you don't have much longer to live. You see that COVID and pneumonia, one of them gonna sort you out. Right? And that's what happened. Sorry, somebody said something, I missed it. Okay. So anyway, but for a normal healthy person who just got a moderate dose of the virus, even if one lobe becomes inflamed and whatever, you have the other lobes of the lung. You might feel a little short of breath, which is what happened to a lot of people. Shortness of breath because of the inflammation of one or two of their lobes. And you feel like low energy because you get a reduction in the amount of oxygen you're taking in. But for the most part, you have the other lobes functioning, keeping you alive until your immune system dealt with COVID, which is why people with a normal immune system pretty much did not die from COVID, right? Anyway, but not just COVID, most respiratory diseases, right? People with normal immune systems will tend not to die from them. So who does the flu kill? Old people. I mean, who in their 20s who catches the flu is ever frets about dying from the flu? If you're 20 years old, you're afraid about the flu? Please. Flu is nothing. It's a minor inconvenience. Why? Because you have a working immune system. Yeah, your lungs are set up to help you to fight them off because of the division. Right? If one lobe can't function, you have four more to go and work it out until the immune system sorts them out, right? Anyway. But never forget, death comes to us all, right? Now, aside from the lovely lobes, I also want to mention this very important structure here in the lung. This is called the hilum or hilus. Now, the hilum/hilus is a term you'll see being used in more than one organ. For example, kidney, you're also going to see hilum. Here's the reason for it. All the hilum/hilus is a specialized area of an organ where the major vessels enter and leave. So pretty much any organ that has a specialized area for allowing the vessels to enter or leave, that area will be called the hilum or hilus, okay? So at the hilum, you'll have, for example, your primary bronchi, the big ones going into the lung. You'll have the pulmonary arteries, pulmonary veins going in. You have the lymphatic vessels as well, right? So the hilum is where you'll find all of these things. So if it's a vessel, it's going in and or coming out at the hilum. So hilum, very important, right? Now, for the most part, that's all I really care about here. We're not really going to be asking you about all of these other things. So for this diagram here, it's just to show you where the hilum is. This is not something I would be throwing down on a quiz and say, hey, what's that, right? So otherwise, don't worry about it. Just remember what the hilum is and what goes into and comes out of it, right? And you'll be good to go. Now, we went through this already, but let's just revisit it real quick. As it says, each lobe is made up of bronchopulmonary segments. So that's the segments we spoke about, right? So you go from primary bronchus, secondary bronchi going to the lobes, and then from the secondary bronchi, you get the segmental bronchi, which are tertiary. And then they go to smaller and smaller segments within the lung tissue. Which is why, as I said to you, you can have one bad spot on the lung in one lobe, one place that is infected, and the rest of the lung is perfectly fine. Right? I mean, there's a reason why sometimes you'll have people with lung cancer suffering from lung cancer for decades before they even realize that they have lung cancer, because the cancer has not been able to damage enough of the lung to severely limit the function of it, right? Unless it metastasizes, in which case that's a totally different story. Anyway, So remember, why we do all of this segmentation? It limits the spread of infection. Right? And because of that, if worse come to worse, as that section of your lung tissue actually die right off, right? Your immune system can, your white blood cells can go in there and pretty much kill everything there and scar your lung, but the rest of the lung is perfectly fine, right? As I said, the smallest division you can see is the lobule, right?
Sir.
So when you look on the, hopefully, Adrian, any other question?
Yes, you were saying that's how the air pass through from primary to tertiary, sir.
So here, remember, air goes from trachea to primary bronchi to secondary bronchi to the tertiary bronchi. The biggest ones are the segmental ones. And then the
Okay.
tertiary ones continue to subdivide all the way down and get smaller and smaller and smaller. Right? Now, when you look at the surface of lung tissue, you're going to see little hexagons, right? Because remember, we said about hexagonal shape, right? It is very efficient. Right? It takes up the least, well, it allows it to take up the most useful amount of space within the organ without leaving too much dead space. You're never going to find a bunch of circles being packed into lung tissue because too much dead air, right? Now, when somebody smokes for a long time, so this is, well, I should mention, this is showing you here now some of the subdivisions. This is, once again, this is another one of these diagrams. It's just there to help you to visualize the branching, but it's not really one that I would ask you questions about, right? So don't worry too much about this one. And this information here, you already know it, so we don't need to go through that again, right? Now, I do want to mention something here, though. It says here, bronchopulmonary segment is a chunk receiving air from a segmental bronchus, right? So remember what I said, the segments are the smallest visible division of the lung, right? It also mentions here that you have this thing called anatomical dead space within the lung tissue. Anatomical, of course, as an anatomy and dead space. What something is dead is non-functional, right? I've never seen a dead functional person. Then again, some people lazy even and they don't even notice. Anyway, and this is within the conducting zone, and it doesn't do anything. And I'm going to explain how that is in a second, right? So let's keep this in mind for now, right? All right. Now, before I talk about the mechanism of ventilating the lungs, of actually breathing in and out, I want to explain to you a little better the concept of the dead space. Because you would think that when you breathe in, the air you're taking into the lungs, you're using all of it. Now, why go through all the trouble of breathing in all of this air if you only want to use some of it? Here's the thing. Let us say, not the right color. Let's see. If it's not blue, then red. That's the way it goes, right? Let us say this here is my alveolus, okay? Air comes into the alveolus. This is, of course, going to be made up of simple squamous epithelium, right? Now, air comes in. What is a good color for air? You can't even see air. Yellow. Why not? So air comes in, okay? So the whole thing gets filled with air. Now, the layer of air near the alveoli surface, this layer right here, so, is what is going to be involved in gas exchange. Let's make oxygen green. Yeah. Let's say the oxygen is green. So the oxygen near to your alveoli can pass through and go into capillaries and do their thing, right? But the rest of this now, oxygen out here, so never gets close enough to the alveoli to move into the body, right? So because of that, we call the middle part the dead space. It's actually a video game named Dead Spaces. Very good game. Anyway. That's the dead space. And why we call it the dead space? Not because it's dead, but because it's useless. So when you breathe in air, you only get oxygen from the functional part of the air that is touching the inside of the alveoli. The middle part, where the rest of the oxygen is, you can't use that. That's why you breathe in 21% oxygen and you breathe out 16% oxygen, because you can't get to the rest of it. If that makes sense. Abby, you have a question? Your mic is open. Okay. So that's what we mean by anatomical dead space. So the more air you breathe in, no matter how much you breathe in, is only the air near to the alveoli is of any use at all to you. The rest of it is in the dead space. So now this, hopefully it makes sense to you, that the smaller the dead space is, the more oxygen you can pull out of the air you breathe in. And the bigger the dead space is, the less oxygen you can pull out. Now that's important with regards to some diseases, like for example, emphysema. Y'all know emphysema? Anybody ever heard of emphysema? Nobody knows emphysema?
No, sir.
What is that, sir? Pus in the lungs?
Yeah, man, it's one of the most common diseases of the lungs. It's very, very common in people who smoke or are around smoke. I think one of the things I said to you was that when it comes to damaging the lungs and smoking, yes, tobacco smoking is one of those that I said, boy, that is the most common cause of lung problems like emphysema. But being around any kind of smoke consistently will cause damage to your lungs over time. Whether it's wood smoke or ganja or whatever it is, it doesn't matter. If you're around enough of it over time, it will damage your lungs, right? I mean, that said, I will say that yes, technically speaking, from a medical perspective, ganja is less harmful than tobacco smoke, right? But it is like saying a 22 bullet does less damage than a 45, which is true. It's still getting shot though, you know? Now, the reason for that is this. It don't matter if it's coal, fire, or whatever. As long as you're breathing in smoke, smoke has particles in it. Coal, wood, plastic, whatever. It no matter. Right? Here's the thing. Let me just try and explain emphysema real quick. Because it's one of these things that might come up. Have it later on in the thing, but let's do it now. Excuse the writing. I'm trying to write with a mouse. Not great. So emphysema. When you take in, let's say, let us say your lung is like this. Let's say this is okay. We have individual alveoli here, right? Each one of them has their little area, all connected by a respiratory bronchiole. So ordinarily, when you breathe in, the air comes in, and then everybody goes into their own little alveolus, right? And then, of course, it means that all of them go near the alveolar surfaces like that. So that's normal, right? So that, of course, means the dead space is only this amount here, so. Right? So remember, this is all good air. This is all going to have gas exchange occurring inside of it, which is what we want. So all that is good. Right? And the dead space is this amount of space here, so. Right? Now, when you breathe in the smoke, remember, no matter where it come from, as long as smoke is invariably will have particles in there, right? So what happens is this. You breathe in the particles. The particles get deep down in your lungs because, you know, people when they smoke, they tend to take really deep breaths in, right? Because they want to feel that smoke deep down for whatever reason. I tried to smoke once in my life and it was quite enough, thanks. All right? One time when I was 17, a friend of, well, I say a friend, but it's more like a friend of me, decided to we're going to buy a pack of cigarettes and teach me how to smoke. That was the last day I looked on a cigarette without feel sick. Right? He made me smoke 4 cigarettes in a row and I vomit out hell. Right? And that was it for me. Anyway, when the smoke comes in, the smoke gets stuck to the surface of the alveoli. And in order to get rid of it, the macrophages come in and they try to clean it off. But sometimes they can't dislodge the particles. And when they can't dislodge the particles, they kill the cells the particles are attached to. Right? So this is normal. Over time, as you smoke, more and more cells are going to be damaged. So you end up now going from this to basically getting this. A big floppy sack. Right? Now, let us try to trace out the dead space in this one now. You have this big floppy sack. So we'll say that there is still useful membranes. And some of it is not going to be useful because some of it will have all kind of particles and stuff stuck to it. But let's say this is actually useful. Why not? Best case scenario, right? All of a sudden, instead of having this much dead space, all of this here is dead space, right? So when you breathe in, the same amount of air comes in, but less of that air is associated now with the respiratory membrane. Less of it you can draw oxygen out of. So you have a massive dead space. So therefore, if you and somebody who's been smoking for a long time breathe in air, assuming you're not a smoker, you get more oxygen out of the same air because they have a massive dead space in the lungs, within the alveoli of their lungs, while you don't have it. Right? This is why you don't see people smoking 2 pack of cigarettes a day, running a marathon and winning. Right? Even if they're fit otherwise, they simply cannot provide their muscles with enough oxygen to maintain themselves. Simple as that. When you look at Olympic level athletes, how much of them you think smoke? None. All right, maybe, yeah, some of them would take a ganja occasionally and whatever. But even that is limited, right? Because emphysema, the damage is permanent. Once you get this big floppy sack, you can't reverse it. So if you have somebody who's been smoking for decades and decades and decades, even if you say, boy, I want to understand this in addition. Well, I mean, blood doping and all kind of thing, you know. You hear about this guy apparently who wants to make a new Olympics for people who take drugs, the drugs Olympics. You can take any kind of performance enhancing drug you want at all in his Olympics. I fully support that. I'd love to see what you could get out of it. You know, I want to see people that fly. Anyway, not to me, it's not. But they take all the drugs they want. I want to see man a long jump and jump like all 60 feet. And that I want to see. Anyway. Now, as the lungs are getting damaged and all of the you're gonna get a buildup of mucus also inside the lung tissue, right? And this mucus will be heavily laden with particles. And it's going to be, and because there are no cilia this deep down in the lungs, it's hard to move it out, right? So what happens now, you have all this nasty mucus sitting down in there. You can't push it out because of the cilia. So you have to try and cough it out. So what happens? You develop what is called the the smoker's cough. They're constantly, and you can hear something, you know, almost like something is in their lungs, like swirling around in there, nice and nasty, right? That's because they have mucus trapped in the lungs and cannot get it out. So even after they stop smoking, they're still coughing, right? You can take all 18 months for the coughing to subside somewhat. But even if the coughing subsides over time, because over time the mucus does diminish, if you're not constantly putting more smoke in there, it doesn't change the fact that they still have emphysema and the damage is permanent, right? So the smoker's cough might go away, still worth it, all right? You come bad dog chase you one day and start huff and puff and see if it's still worth it when them yam you. Anyway, right? I understand vice, right? I understand addiction. I myself have an addiction. I'm very much addicted to sugar, and I know, right? One day sugar will kill me. So I understand the sentiment, right? Now, hopefully this emphysema thing, remember, it doesn't necessarily, I'm not talking specifically about tobacco. People who do charcoal burning, the same problem they have over time, okay? Keep that in mind, right? All right, that said, let's now talk about how you actually breathe in and out. Luckily, this should be easy to explain because y'all would have done this at CSEC, right? All right, let's talk about inspiration and expiration, right? As respiratory ventilation, as we know, right? Now, there are two ways to breathe, to ventilate your lungs. The first one is called quiet breathing. Right? Quiet breathing. When you're not exercising, when you're not under any stress, your body is breathing at its normal pace. We call that the quiet breathing. And quiet breathing is super, super simple because you only need to use your muscles to breathe in with quiet breathing, right? Now, here comes the CSEC information to remind you. In order to quiet breathe in, here's what you do. There are two muscles involved. You have the diaphragm and you have your external intercostal muscles, right? So far, so good, right? When you want to breathe in, here's what happens. The diaphragm contracts. Normally the diaphragm has a dome shape and it presses up against the bottom of the lung, right? So you can see the diaphragm here. This is its original position. It's pressing up against the bottom of the lungs, right? So it touches the inferior aspect of the lungs, if you want to have a nice way of saying it, right? When the diaphragm contracts, it pushes down. So we say the diaphragm flattens out. So the diaphragm moves down to here, right? Now here's why that's important. When you move the diaphragm from touching the lungs and flatten it out, you have now introduced more space inside your chest cavity, right? So you're adding more space inside your chest. Remember, your chest is a closed system. There is air in the chest, but that amount, the air that is in the chest can't leave and can't be gained. It's right. It's been there since before you're born, right? I mean, obviously, you add to it over time from the blood, but we won't get too deeply into that. But for the most part, it's a consistent volume of air. So by moving the diaphragm down now, you've made the chest cavity bigger, right? Then the next thing that happens now is that your external intercostal muscles contract. And when they contract, when you breathe in, you notice your rib cage goes up, right? It also pushes out a little bit. So as I say, breathe in, you go up and out. And what you're doing is you're raising the rib cage and pushing it forward. And when you do that, you also increase the space inside the chest cavity. So the diaphragm is contracting to increase space in the chest cavity. The external intercostal muscles are contracting to increase space inside the chest cavity. All of this is to give more space. And with the extra space, what happens? The pressure inside your chest cavity is going to drop, right? Now, hopefully this all sounds familiar to you from CSEC, right? So remember now, the reason why we're doing all of this contracting here and there is because we're trying to drop the pressure. Okay? So now, so you go from this to this, and from this to that. Bigger space. Now, here's the thing. Because there's more space now in the chest cavity, the air in the chest cavity is going to spread out because there's more space for it to go, right? As the air spreads out, the pressure inside the chest cavity is going to drop. Okay? Now, remember, this is important. Bigger space inside the chest causes the air in the chest to spread out. The spreading out air causes the pressure in the chest to drop. When the pressure in the chest drops, the pressure inside the lungs is now greater than the pressure inside the chest. And that causes the lungs themselves to expand into the chest cavity, right? As the lungs expand into the chest cavity, the air in the lungs expands too because there's more space for it, which means pressure in the lungs now drops too until the pressure in the lungs is lower than the pressure in the air, right? And of course, things always move from high pressure to low pressure. So when the pressure in the lungs is now lower than the pressure in the air from outside rushes right in. And hence you breathe in. I am hoping that sounds familiar to you, right? In order for you to breathe out, all you have to do is relax your diaphragm. It goes back to its original position. You relax your external intercostal muscles. Your ribcage drops down and goes back in. And these, of course, increase the pressure inside the chest cavity again. And because now your lungs are bigger than before, so they take up more space, it also now means that the pressure inside your chest cavity increases now because you have the same amount of air as before in a smaller space. And the lungs are squeezing the air, so the air squeezes the lungs, right? 1 second. Normally when you hear somebody's chest is getting tight, it's normally associated with some sort of asthmatic attack, right? What is usually happening when you see people get their chest get tight is that you have the bronchi or the bronchioles constricting. And the tightness you feel is the muscles of the bronchioles squeezing down on the bronchioles. If that makes sense to you, right? But you can't normally feel the lungs being compressed because your body tends to deaden sensations that repeat very often, and if they're not dangerous, right? So you for the most part, you can't feel the lungs as they deflate and inflate, right? Now, so remember now, the increased pressure, because the lungs are bigger, so the air in the chest cavity squeezes down on the lungs, then the lungs squeeze down on the air inside them, which now means the pressure in the lungs is higher than the pressure outside, and the air gets pushed out. And you breathe out. So that's quiet breathing. Quiet breathing only needs the contraction of the external intercostal muscles and the diaphragm. In order to breathe out, you just have to relax them. Okay? All right.
Sir,
So, yes.
could you please repeat a little bit from when you said the bigger the space in the chest cavity leads the pressure to spread out? Can you repeat from that?
All
If
right.
that's what
The
you
idea
said?
here is that when you're breathing in, the diaphragm moving down increases the space inside the chest. The rib cage contracting and lifting and pushing out increases the space inside the chest, right? So we want to increase the space inside the chest cavity. The air inside the chest cavity now has more space when you breathe, when you do that. So the air spreads out. And as the air spreads out, the pressure in the chest cavity is going to drop. Because you don't have this, because now the amount of air in the chest is now scattered more widely. So it generates less force. So therefore the pressure drops. Right? So as the pressure drops, what happens? The lungs now are now sitting in the chest cavity, and the pressure around the lungs drops too. So what do the lung tissue do? Just the same way the air in the chest cavity would have spread out, the lungs also wants to spread out. So the lung expands in that extra space. And the pressure inside the lungs is going to drop too, because of course the lungs are now bigger. And the air inside the lungs will spread out too, just like the air inside the chest cavity. And that causes the pressure in the lungs to be lower than the pressure in the air. And air, of course, rushes from outside in the atmosphere down into the lungs to take up the extra space. And that is breathing in. Right? Hopefully y'all remember that from CSEC, right? Now, the next type of, all right, I guess this is going to be the last slide. The next type of breathing in is called forced breathing. Right? This is now you're exercising, you're running out of oxygen, your body needs more oxygen at a faster rate. So your body has to now do what is required to pump that oxygen in faster, right? So you need to take in deeper breaths, stronger breaths. That is forced breathing now, right?
The one before this.
Abby, you had a question?
Are you on the phone?
Okay, I don't know what's going on there. So here's how you push air into your lungs when you're trying to breathe in. You're still going to have the external intercostal muscle contracting.
Hello, sir.
Go ahead.
What did you say the first breathing was regarding pressure?
The first one is quiet breathing. Now we're looking at forced breathing.
Oh, quiet. Oh, thanks.
Right. So the diaphragm still contracts. The external intercostal still contracts. All of that still happens, right? But now you're going to have more muscles involved. So in order to make you breathe in even more deeply, you're going to have these muscles all contracting at the same time. What these muscles do is that they make the chest cavity even bigger than before, right? They're all going to be pulling on the thoracic cavity, increasing the space inside the thoracic cavity, which of course means your lungs expand even more than normal when these muscles get involved. So the pressure inside the lungs drop even lower than normal. So even more air will rush in when you're doing forced breathing. I mean, the thing with forced breathing is that you can force yourself to force breathe. You know, if the doctor tells you to take a deep breath, you can take a deep breath in, right? And if you take a very, very deep breath in, you can feel pressure in your back and your chest and your neck and all about. Why? Because you have extra muscles contracting, and those extra muscles are what you feel. Also, if you haven't exercised for a while and you go for a run or something, and you get a stitch in the side and a pain in the back all over the place, these are the muscles that you are straining because you're not used to exercise, they hurt, right? So you have the scalenes, sternocleidomastoid, the pectoralis minor, and the quadratus lumborum and erector spinae. Now, you all did muscles last semester, so you all know where to find these muscles, I'm sure. Please remember, these are involved in forced inspiration, breathing in, right? So remember, the purpose of these muscles is to make the chest cavity bigger, so more air rushes in. So when you're forced breathing, your breath comes in larger volumes, right? And we call these muscles accessory muscles. And we need them, remember, to breathe in. I'm stressing it, of course, because there will be muscles associated with breathing out, right? And a nice, easy multiple choice question is just to mix up the muscles to breathe in and breathe out and say, hey, which ones belong where, right? So keep that in mind. All right, it's 5:17, so I'm gonna stop. So next Tuesday, of course, I will be in the place. So I'm told we have a lot of work to do. Now, with regards to what I will be collecting next week. Tutorials, yes. All right. Y'all have a chance to go through the last tutorial I sent yet? Because I want to send a respiration tutorial. I want to assume silence means consent, right? The last one should have been lymph, yes. All right, so remember, bring the tutorials when they come in next week. Also remember, next week, Wednesday, we are going to be doing, what do you call it there? Your first lab quiz, and that lab quiz is going to be on blood. I decided still to do blood only, and do a combo lab quiz the following week, right? So remember the blood PowerPoint. Remember all the things in the blood PowerPoint. Please make sure you review them, right? Yeah, man, next week is face-to-face, right? And the week after is also face-to-face. And in the labs, we don't have a lot of time because we have other things to do. I'm going to give it a hearts to dissect. I want to do the blood typing test. We have to draw a section of the trachea from slides. There's a whole heap of work in the lab manual to complete, but I'll probably let you bring that in the following week. All right, tell you what I'm gonna do. Boo, all you want is to get done. I'm gonna say, all right, I won't sign any lab manuals next week. I'll sign them the following week, right? But I need you all to start finishing up what's in the lab manual. So I want you to finish up everything between blood and the lymphatic system for the following week.
Could you take back the lab manuals?
Yeah, man,
This
yeah,
one
man.
next
No, I realized some of you didn't get them. When I come,
Okay.
that's one of the reasons I decided to make it go over to the following week. So I'll
Perfect,
I'll
thank
bring
you.
them back next week, no problem. Right? So remember,
How many questions is the test?
test or lab quiz.
The quiz, yeah.
It's not a test, it's a quiz, right? You're looking at about what, 15 questions, I think it is.
Multiple choice, right?
Don't you like surprises?
No,
Yes,
sir.
You don't want us to come and find out?
Sir, sir,
No, sir, we don't.
Spoil sport. It will be a mixture of short answer and structured questions.
So it's a test then, sir. All right.
No, it's a quiz. A quiz is not a test. It's a quiz.
And structure or short
answer and MCQ.
It will be short answer and MCQ. Short answer, of course, can include matching. It can include one answer questions. It can include one sentence questions. Diagrams to label, stuff like that. Yeah, the in-course test. Yeah, I'm kind of leaning towards letting Kingston do their in-course test first and then doing yours. Um, I, I like the idea
Sounds like a plan, sir. Sounds like a plan.
yeah, I enjoy the idea of people scrambling madly to find somebody in the Kingston for ask them what them get. And when them come and exam and realize it's something totally different, that would be hilarious. Anyway,
No, sir, they not tell me, man. They not tell me.
of course, I wouldn't tell you that. Me must suffer, you must get through, you must be mad. You know the whole of we suffer now, or none of we suffer, no, sir?
No, sir, I 1 degree now, sir. I know 1 degree, if you say I'm more than 1 degree. Yeah,
Yeah,
also.
I'm more than 1 degree, but guess what? You have first class, second class, and pass. All right, that's all I'm ever say. Why you must get one first class after my work and me must get one pass? You lucky. Either whole of we get pass, or everybody get first class. Anyway, folks, I got another class shortly, so let me let you go. Remember, next week, Tuesday, I will post the first respiration tutorial, and we'll go through that in class on Tuesday. Come prepared. Remember, we will be dealing with samples, which means I need to see if I didn't get a chance to see if there were gloves down there. Are there gloves? Y'all have gloves down there, right? When you do the
Yes, sir,
biochemistry
we
lab, you all have gloves, right?
I
I need to never need to bring gloves
microbes.
down
Sir,
with
you
me.
can carry gloves, sir, of all sizes.
All right, I'm gonna try big some gloves from the lab on campus. But yeah, so we'll be doing some drawing,
Yes,
we'll be
sir.
doing some dissecting, we'll be doing some bleeding on Tuesday. All right, folks.
Sir,
Oh, you make
On
it sound
Tuesday,
so
sir.
Yeah,
simple.
man. No,
Thank
sorry,
you.
Wednesday. Otherwise, folks, I will see you all next week. Have a good weekend.
bye, sir.